This video involves the derivatives of the trig functions. So that's what we'll call it, the derivatives of the trig functions. So we're going to look at the derivatives of all the standard trig functions that you know. I'm going to remind you of a couple of limits that you had. One of them was the limit as x goes to 0, sine of x over x equals 1. And then there was a second one, the limit as x goes to 0, cosine of x minus 1 over x equaled 0. Of course, if that's turned around, that's 1 minus cosine of x over x. That's also 0. It's just the negative of this thing anyways. I'm going to do approximately half of the derivatives, deriving the formulas for the derivatives, and leave the other half of them to you. So, since most books take the derivative of sine of x as a standard example, I think I'll choose cosine of x. So let's first determine the formula for the derivative of cosine of x. According to the derivative formula, this is the limit as h goes to 0. Let me write that out. The limit h goes to 0, cosine of x plus h minus cosine of x all over h. Now, one thing I think I should probably warn you about is that I'll liberally use the trig function rules, identities, things like that. Most calculus books feature a review section in the first chapter of the book, or they have something in the last appendix or something like that. This course, I'm not going to really review trig things, but if they're extremely necessary in the context of a problem, I will feel it necessary to remind you. So with that in mind, the first thing I'm going to do is use the sum rule, sum of angles rule for cosine. I'll write it out in detail. Hopefully that also, whenever I write them out in great detail, I hope that reminds you. The way you do it is it's the cosine of the first angle times cosine of the second angle minus sine of the first angle times a sine of the second angle. All that is minus cosine of x. So let me read it for those with vision impairments. I have the limit as h goes to 0 of cosine of x times cosine of h minus sine of x times sine of h minus cosine of x all over h. Now I'm going to cobble some things together. For example, I notice that there is a cosine of x in the first and last term. So I'm going to put those close to each other. So the limit as h goes to 0, cosine of x, cosine of h, minus cosine of x, minus sine of x, sine of h, and the entire thing is over h. Now I'm going to break it up into two pieces. The limit as h goes to 0, cosine of x, cosine of h, minus cosine of x over h, plus, no, sorry, minus, there's a minus sign up there, minus the limit as h goes to 0, sine of x, sine of h, all over h. Now you know that you can generally take the limits of each and every part unless you get things like 0 over 0. So for the first half of this, I'm going to factor out a cosine of x, and I end up with the limit as h goes to 0, cosine of x times cosine of h minus 1 over h minus the limit as h goes to 0 I'm going to pull the sine of x out front just to make what I'm doing more evident. Sine of x times sine of h over h. Now you can break each of these limits up. For example, the limit as h goes to 0 of cosine of x is still cosine of x, because there was no h in the function itself. The limit treats it like it's a constant, because there's no, as far as the limit's concerned, h is the variable, x is not. Now the other one, the limit as h goes to 0 of cosine of h minus 1 over h, well, that's 0. I'll copy down my minus sign. Same thing as before, the limit as h goes to 0 of sine of x is sine of x. And the limit as h goes to 0 of sine of h over h equals 1 times 1. And let me finish this up then. Cosine of x times 0 is 0, of course, so I end up with just negative sine of x. So I get the derivative, d over dx, cosine of x equals negative sine of x. You might try the same thing yourself instead of looking right to the book or going online or whatever. Try to verify on your own that the derivative of sine of x equals positive cosine of x. I want to emphasize the plus in front of it, because one of them is, they're not exactly the same, they're not symmetric. One of them is positive and one of them is negative. So those are the most important rules, obviously, because everything else is defined in terms of sine and cosine. So while we're at it, let's do tangent. The derivative. Now I think about it, tangent is often done. So I'll tell you what I'm going to do. I'm going to do the derivative of cotangent of x. Now the derivative of the cotangent, well, cotangent is equal to cosine of x divided by sine of x. Now, as you might be guessing, I'm going to use the quotient rule for this. So the way the rule works is we take the derivative of the numerator, which is cosine of x, times the denominator, sine of x. So you have the derivative of cosine of x times, leave sine of x alone. Then this has a minus sign in its formula. Next, you want to leave the numerator alone, cosine of x, times the derivative of sine of x. And all of that is over sine of x squared. So that's the basic formula for the quotient rule. Now, as we've just learned, the derivative of cosine x is negative sine of x. So I have negative sine of x times sine of x minus cosine of x, and the derivative of sine of x is cosine of x. And the denominator, I'm just going to write sine of x a little bit differently. You realize that sine of x squared is the same as sine squared of x. For some reason, we seem to like that notation better. Here's what I have then. In the numerator, I have negative sine squared of x minus cosine squared of x divided by sine squared of x. I'm going to factor a negative 1 out of the numerator. What's left is sine squared x plus cosine squared x. All of this is divided by sine squared of x. Well, the sine squared of x plus cosine squared of x, even if you didn't understand your trig, you know that that thing equals 1. So I have negative 1 times 1 in the numerator. All of that is over sine squared of x. And so my derivative rule, d over dx of cotangent of x, equals negative cosecant squared of x. Remember, 1 over sine is the same as cosecant. Likewise, the derivative for tangent of x equals secant squared of x. There's, in some way, shape, or form, I suppose there is some symmetry here. It's just not perfect symmetry because of those negative signs. And to help remind you, I'll put a plus sign in front of secant squared, just so you know that one is negative and one is positive. Now we have two last trig functions. Let me do the derivative, d over dx, of cosecant of x. Well, that's d over dx of 1 divided by sine of x. And then I'm just going to use the quotient rule. So that gives me d over d of x of 1 times sine of x minus 1 times d over dx of sine of x. All of that is divided by sine squared of x. So let's simplify this numerator. D over dx of 1 is 0, so I get 0 times sine of x minus 1 times the derivative of sine of x is cosine of x. All of that is over sine squared of x. And this cleans up to be negative cosine of x divided by sine squared of x. Now the derivative is never written that way. Instead, what's done is this. Usually we have negative cosine of x divided by sine of x times 1 over sine of x. That's not the way it's left either. The formula is usually written this way. The derivative, d over dx of cosecant of x equals negative cotangent of x times cosecant of x. Similarly, the derivative, d over dx of secant of x equals secant of x times tangent of x. So you can see there's that symmetry again, somewhat symmetry, but not quite as exact as we want it. So let's do some examples with all this stuff. So as an example, what is the limit as x goes to 0 sine of 5x over 3x? First of all, this is the way it's written in the book, but you got to remember, this is the sine of 5x. I would prefer that they put parentheses around it, but they do not. Now, what I somehow want to make use of is that the limit as x goes to 0, sine of x over x equals 1. Well, inside the sine of x is a 5x. So what I need, I'm writing off to the side here, limit as x goes to 0. If I can get sine of 5x over 5x, that equals 1. Because as long as I have the same thing in the parentheses as I have in the denominator, and they're both going to 0, that's what this limit is. So what I'm going to do is try to force a 5x in that denominator. Here's how you do it. The limit as x goes to 0, sine of 5x. Now in the denominator I have 3. I'm going to write it as 3 times 5 of x, 5x. But then I'm also going to multiply by 5. So the net effect of what I did is I multiplied it and divided by 5. But what's more important is that this 3 and this 5 in the numerator, the 3 in the denominator and 5 in the numerator, will come out front because it'll be unaffected by the limit. And then I have the limit as x goes to 0, sine of 5x over 5x. That's exactly what I need to have. So this is 5/3 times 1, which equals 5/3. I'm not going to do any of these things with the calculator. It's all going to be algebra to show you the kind of stuff that we jump through to make these things work. You'll find too, when you're working with your calculator, there'll be some things that'll actually give your calculator an error, and using calculus you'll be able to do things your calculator cannot. Let me go on to my next limit. The limit as x goes to 0, tangent of 7x divided by sine of x. Well, this is tough. I think because the limits that I gave at the beginning of this lecture, let me scroll up to them again. We have the limit is sine of x over x equals 1, cosine of x minus 1 over x equals 0. I'm going to try to make things like that happen within these problems. And whenever you're dealing with tangent, since my limits are in terms of sine and cosine, I might as well rewrite this as the limit as x goes to 0. Tangent is going to be sine of 7x divided by cosine of 7x. All of that is divided by sine of x. As I've been harking on this over and over and over again, think of that sine of x as over 1 so that you know what to do next. This will become the limit as x goes to 0, sine of 7x divided by sine of x times cosine of 7x. So here I am a little bit stuck. What am I going to do here? Well, this is one of the things you can do. What I'm going to do is I'm going to break this up into 3 individual limits. So what I'm going to do is I'm going to have the limit, but I want them all in a fraction format. So I can do the limit as x goes to 0 of sine of 7x, and I'm going to put it over 1 just for now. Then I have the limit as x goes to 0, 1 over sine of x, times the limit as x goes to 0, 1 over cosine 7x. Now I can actually make this a little bit simpler. With the trig functions, you're allowed to plug the number directly into the function so long as it's defined. So let's take a look at what happens here. The only one I know right now, this last piece here, the limit is x goes to 0, 1 over cosine of 7 of x, is the same as 1 over cosine of 0. That's 1 over cosine of 0, and that equals 1. Cosine of 0 equals 1. So right away I have something working there. So the limit as x goes to 0, sine of 7x over 1 times the limit as x goes to 0, 1 over sine of x. Now, this is a tricky situation because when I look at these other 2 limits, I can plug 0 in for the first limit and get sine of 0, which is 0. However, if I try to plug 0 into the second, so let's take a look at this. Sine of 0 is 0, but down here having a sine of 0 is not going to cancel this one out. They're both of these have the variable involved. That means they're changing values as x changes values. So, truth be told, I should have never ever broken those up, because both of the individual limits do not exist. So I've got to put those back together. So I'm not exactly sure how you want to mark this. Let me just say in here, I shouldn't have done that. Should not have done that. All of those rules are only so good as the limits existing. So let me put it back together. Here's what we have. The cosine part I don't have to worry about, it's gone. I'll have the limit as x goes to 0. I am going to keep it as sine of 7x over 1 times 1 over sine of x. The reason why I want to do that is because I need to get a 7x in the first fraction. Under here I need a 7x. So what do you normally do? Force it in. This is the limit. So x goes to 0. Sine 7x over 7x. Now, to make up for what I forced into that spot, I can multiply the second fraction's numerator by 7x. Now I'm getting somewhere. The 7 that's in front of the 7x, I can literally bring it out to the front of the limit, because the limit doesn't do anything with a constant. So anyways, I'm going to get 7 times the limit as x goes to 0, sine of 7x over 7x times x over sine of x. And now I have what I want. The 7, of course, is 7, but the limit as x goes to 0 of sine of 7x over 7x is equal to 1. As is the limit of x over sine of x. It's just 1 over 1 but turned upside down. So the end result is this equals 7. Moving on. Move this to the top of the page. Another example. I got tons of examples. We'll just see how long I go for before I think you've had enough. Let me see. The limit as x goes to -3 sine of x plus 3 divided by x squared plus 8x plus 15. Well, the first thing you want to try to do is just plug in the numbers. So if I try to do that, I'll have sine of -3 plus 3 divided by -3 squared plus 8 times -3 plus 15. That gives me sine of 0 over 9 minus 24 plus 15. Sine of 0 is 0. So I get 0 over 0, and I can't do that then. So let's cross that out. That would not have worked. But I do know now, since -3 is a 0 of the denominator, I know that x plus 3 has to be a factor. So the limit as x goes to -3 sine of x plus 3 over, so the denominator will factor as x plus 3 times something. Now what that other thing is not going to be hard to figure out. I know that the quadratic in the denominator was x squared. It started as x squared, so my first other piece has got to be x, and it ended with plus 15, so I have to have plus 5. Now I can break this up. The limit as x goes to -3 sine of x plus 3 over x plus 3 times 1 over x plus 5. The first part, sine of x plus 3 over x plus 3, the limit as x goes to -3, is equal to 1. Since you have exactly the same thing in parentheses as you do in the denominator, and they're both going to 0. However, on the other piece, I can now simply plug the -3 in. So I'll have 1 over -3 plus 5, and it looks like my entire answer is 1/2. Alright, let's do some derivative examples. Let's start with the derivative d over dx of 1 minus sine of x divided by 1 plus sine of x. I recommend that you write the rule every single time you do a problem, at least for a while, because then you'll memorize the rules without really thinking that you had to think about it or have flashcards or anything like that. You simply write this every single time. In the numerator, we have d over dx. Now you take the derivative of what was in the numerator, 1 minus sine of x, times 1 plus sine of x, and then minus, now you have 1 minus sine of x, times, let me move the page over a little bit, the derivative, d over dx, of 1 plus sine of x. And all of that is over 1 plus sine of x squared. All right, let's go ahead and compute all those then. That equals, the derivative of 1 minus sine of x is negative cosine of x. And that'll be times 1 plus sine of x. Fix that plus to look like it. Then I have minus 1 minus sine of x times cosine of x. And all of that is over 1 plus sine of x squared. As I've mentioned several times, this is enough for an answer if you ask me. If you put that on a test, you'll get full credit. I can tell what you did. All your steps are shown. However, if this came from a textbook, and in fact it did, and you finished and got your answer and you went to the back of the textbook, it's not going to look anything like this. They're going to simplify. So for this once, let me simplify. I'm going to multiply my negative cosine through. So I have negative cosine of x minus cosine of x sine of x minus cosine of x. And for the last part, a lot of people tend to make a mistake here and put the wrong sign. You have a negative times a negative. It's going to cancel out and give you positive cosine or sine of it. Plus, sorry, sine of x times cosine of x. And all of that is over 1 plus sine of x squared. Notice there is some stuff that cancels out. I have negative cosine of x sine of x and sine of x cosine of x. So I get negative 2 cosine of x all over 1 plus sine of x quantity squared. Let's try d over dx of x sine of x all over 1 plus cosine of x. That's going to equal d over dx of x sine of x times 1 plus cosine of x minus x sine of x times d over dx of 1 plus cosine of x. All of that is divided by 1 plus cosine of x squared. And let me go ahead and... Now, I don't know how much you want to do in your head, and this is one of those ones, if you look, the d over dx of x times sine of x, that is a product. And the product rule says for that piece, I should take the derivative of x times sine of x plus x times the derivative of sine of x. And that's still multiplied to 1 plus cosine of x. So I had to use a product rule inside of this quotient rule. Minus x sine of x. The derivative of 1 plus cosine of x is negative sine of x. And all of this is over 1 plus cosine of x, that quantity squared. Alright, let's go ahead and do our derivatives. The derivative of x is 1. So you have 1 times a sine of x plus x times the derivative of sine of x, which is cosine of x, times 1 plus cosine of x. It looks like I'm going to plus x times sine squared of x. All of that is over 1 plus cosine of x squared. Now actually, I would have been happy, yeah, I would be happy right here. There, you finished it off. I see all the derivatives and everything like that. Nonetheless, I think I might get a little canceling going if I multiply some things out. So let me simplify a little bit. You don't have to. You can sit back and enjoy. The first parenthesis becomes a sine of x plus x cosine of x times 1 plus cosine of x plus x sine squared of x. Well, the reason why I'm even thinking of multiplying out is because I see a sine squared, and a lot of times wherever there's a sine squared, there's a cosine squared lurking somewhere, and that when you add the two of them together, you just get 1. So let me FOIL out the first two parentheses. I'm going to get sine of x times 1. I'll kind of do it with my pointer or my mouse. Sine of x times 1 will be sine of x. Then sine of x times cosine of x. We get plus sine of x cosine of x. And then I have x cosine of x times 1, so I'll get plus x cosine of x. Then finally, I'll get x cosine of x times cosine of x. So I'll get plus x cosine squared of x. But then I have plus x times sine squared of x. See, I told you. So, and all of that is over 1 plus cosine of x squared. Well, this piece here, this x times cosine squared plus x times sine squared, I can factor out an x and write it as x times cosine squared of x plus sine squared of x. And of course, cosine squared plus sine squared is always 1. So what I'd probably put for my final answer is going to be sine of x plus sine of x cosine of x plus x cosine of x plus x. Because that is, after all, x times 1 divided by 1 plus cosine of x squared. So let me go ahead and box that off as my answer. Here's another one. Might be interesting. Let's try this. d over dt, just to get used to whatever I'm seemingly dividing by. When you see that dt, then the functions you see will all be in terms of t. So it's no surprise I'm going to have tangent of t divided by 1 plus secant of t. From d over dt, tangent of t times 1 plus secant of t minus 1 plus secant of t times d over dt of tangent of t of, whoops, get that out of there. That was tangent of t times d over dt of 1 plus secant of t. And all of that is over 1 plus secant of t squared. The derivative of tan is secant squared t times 1 plus secant t minus tangent of t times the derivative of 1 plus secant of t is secant of t times tangent of t, and all of that is over 1 plus secant of t squared. That's as far as you got to go, but I'm going to see if I can do any kind of simplifying. It doesn't, to be honest, I don't really see it here. I see if I even multiply this out here, I'll get secant squared, but then I'll have secant times tangent squared. I'll tell you what, here's what I'll do. I'll put a little star, because you do not have to do this, but I think it is beneficial as a learning exercise. I'm going to get secant squared of t plus secant cubed of t minus tangent squared of t times secant of t all over 1 plus secant of t squared. Notice I am going to, here's what I'm going to do. I don't know if you remember the formula for tangent squared, but secant squared t plus secant cubed t minus tangent squared of t equals secant squared of t minus 1 times secant of t. So this here is an identity that I made use of. Tangent squared is the same as secant squared minus 1. The reason I'm thinking of doing that because I see a secant cube that I wouldn't mind getting rid of if I could. Alright, let's continue here. I have this equals secant squared of t plus secant cubed of t. There, and then I have, use the mouse here, minus secant squared times secant gives me minus secant cubed of t. And then finally I have minus secant t, so plus secant t. All over 1 plus secant t squared. So the secant cubes cancel out. Oh, look how cute. I can take out a secant t from what's left over, and I'll have a secant t times a secant of t plus 1. So I took secant from secant squared, left me with a secant t, and then the secant, when I took it away, left me with 1. The reason why I particularly like that is because the denominator is 1 plus secant t squared. Well, I can cancel secant t plus 1 and one of the 1 plus secant t, and I end up with secant t all over 1 plus secant t. And that's what I put for my answer. Let's try d over d theta. That means my functions will now have to have thetas instead of x's. I'll have 1/2 e to the theta times cosine of theta. The 1/2 doesn't mean anything. It'll just come out front. But e to the theta times cosine of theta, I'll use the product rule for that. So I'll have d over d theta of e to the theta times cosine of theta plus e to the theta times the derivative d over d theta of cosine of theta. This equals 1/2, and in the parentheses, e to the theta cosine of theta plus, I didn't make that theta-ish last time. Well, let me put it, there we are, e to the theta. The derivative of cosine of theta is negative sine of theta. And there's a perfectly fine answer. I'm nonetheless going to factor out an e to the theta, and I'll get e to the theta over 2 times cosine of theta minus sine of theta. And that would be what I would give as my final answer. And then one last example. Let me pull up my note here. We want to do find an equation of the tangent line to y equals cosecant of x at x equals pi over 4. We fix that pi. The pi looks kind of silly. Pi over 4. So what are the two things you need for such a problem here? You need a slope, which we get from the derivative, and I need a point. Let me start with the point. I already know the x value, and that's pi over 4. Well, what's the y value? Well, cosecant of pi over 4 You probably don't memorize cosecant or any of the other functions like that. But you should remember that cosecant is 1 over sine. And sine, so it's 1 over sine. Sine is radical 2 over 2 there. So you flip it and you get 2 over radical 2. So my point is pi over 4, 2 over radical 2. And some people may even simplify that. A lot of people hate 2 over radical 2, and they simplify it to be, let's see here, multiply numerator by denominator by radical 2. So I would have 2 radical 2 over 2. Okay, so instead of 2 over radical 2, I'll use radical 2. So there's my point. Now how do I get my tangent line? I need to take the derivative. So dy over dx at x equals pi over 4 equals, well, the derivative of cosecant is negative cosecant cotangent. And I plug in pi over 4 for each of those. Okay. Well, negative cosecant of pi over 4 is simply negative radical 2. Cotangent of pi over 4 is 1. So the slope is negative radical 2. So I have my point. I have my m. So we use y minus y0 equals m times x minus x0. That'll be y minus radical 2 equals negative radical 2 times x minus pi over 4. Be honest, if you're going to try to put this in slope-intercept form, I see no benefit to doing that other than the fact that you're going to plug it into a calculator to check your work. And that's precisely what I'm going to do here. So I'm going to graph y equals cosecant of x. And at the point pi over 4, I'm going to see if my tangent line works. The way I can put it in my calculator or my computer is I have to solve for y. So I can simply write negative radical 2, have x minus pi over 4, and then plus radical 2. You too can put it in your calculator that way. I'm going to use a little different grapher than I know you use, but nonetheless, hopefully you would download this thing. It's free. For my function, insert function, it does take CSC, but I have to put x in parentheses. So there they are. You've seen this thing probably a million times. And for my second one, I want to graph negative SQRT of 2, putting that in parentheses, times x minus, you actually spell pi, pi, slash 4, parenthesis, plus SQRT of 2. And to make sure I'm in the right spot, it certainly does look like I'm in the right spot. I'm going to zoom in on the area where it strikes the graph. I'll move this piece to the middle, and I'm going to zoom in for a little bit. And we'll see if I'm right. You can see that it's certainly tangent there somewhere. I could change my my numbers to be trig-related numbers, but instead what I'm going to do is I'm going to insert a point series, and my point was pi over 4, and the y value was the square root of 2. And let's see, I'll put a nice fat black dot there. Okay. And you can see right here, the graph is touching at just that one piece. Let me take a picture of that. So that point right there is pi over 4, comma, radical 2. The curved graph is y equals cosecant of x. And the straight line is y equals negative radical 2 times x minus pi over 4 plus radical 2. So that tells you everything you need to know about that graph. As you might understand, we're going to be delving in pretty heavily into more detailed views of graphs and smaller wiggles and things like that that you've never done before. So until then, I'll go ahead and sign off for tonight. Talk to you next time.